Hi everyone. So in this video, I'm going to discuss one of the most common technologies that is used to connect the local area networks, which is the IEEE 802.3 standard, also most commonly called as Ethernet. So let me talk about Ethernet, the different varieties of Ethernet, and also its frame format. What are the fields does it consist of? All those things. So starting first, Ethernet is probably one of the most ubiquitous computer network that is in use today, with the other one being the WLAN to connect local area networks. Ethernet, in contrary to your WLAN, uses physical communication links. So it uses wired communications, which include twisted pair cables, fiber optic links, or even coaxial cables. Ethernet operates in the data link layer and also in the physical layer. Traditionally speaking, Ethernet, there are two types of Ethernet. The first Ethernet, or the early stages of Ethernet, we call it as a classic Ethernet. This is the actual original form of Ethernet, and it used to run between the rates of 3 to 10 Mbps. It has now become obsolete. You don't find it anywhere. The modern day Ethernet, also called as switched Ethernet. The reason why we call it as switched Ethernet is because we use switches to connect different computers. This has the capability to run at different speeds, 10 Mbps, 100 Mbps, 100 Mbps, 1000 Mbps, and 10,000 Mbps. And the names are also given as fast Ethernet for 100 Mbps speed, the gigabit Ethernet, which runs at 1000 Mbps speed, and 10 giga Ethernet, which runs at 10,000 Mbps. So this we also call it as the evolution of Ethernet. Okay, starting from the classic or standard Ethernet, which runs at 10 Mbps, forwarding it on to 100 Mbps, 1000 Mbps, and even 10,000 Mbps. Now, in this particular thing, before we delve into the frame format and stuff, let us just discuss about some of the history of Ethernet. So Bob Metcalfe and David Boggs, these are the two people who actually designed and implemented the first local area network. They also published a paper, Metcalfe and Boggs, in 1976. This particular model used a single long thick coaxial cable, and it ran at 3 Mbps speed. They called this system, or the name of the system, Ethernet, from the name ether. Ether is nothing but the luminiferous cable through which the electromagnetic radiation was once thought to propagate through. So they named this particular network after the cable they used to connect the different systems. If you see, this is the actual original diagram which was drawn by Dr. Robert Metcalfe in 1976 to present the Ethernet idea to the National Computer Conference in June of that particular year. On the drawing, you can see the original terms which are used for describing the Ethernet. There are terminators. There is a vampire tap here. This is the ether, which is the long cable which is used to connect the different systems. You see an interface. You see the stations here. Okay. Now, they are the DEC, Intel, and Xerox company. DEC is one company, Intel is one company, and Xerox is another company. They drew up a standard in 1978 for a 10 Mbps Ethernet called the DAX standard. They actually defined a frame format for also for this Ethernet also, which we call it as a DAX standard for Ethernet. But when IEEE came along, because of the publicity and wide usage of this particular frame format, they decided not to make many changes, and they adopted the same model with some minor changes. So with some minor changes, the DAX standard became the IEEE 802.3 standard in 1983. So classic Ethernet snaked around the building as a single long cable to which all the computers were attached. The first form of classic Ethernet is called as the thick Ethernet. The first variant of Ethernet is also popularly known as the thick Ethernet, which resembled a yellow garden hose with markings for every 2.5 meters to show where to attach the computers. There is a second variant which is called as thin Ethernet, which is slightly smaller in size and which can be bent more easily, and it is much more flexible when you compare with it with the thicknet or the thick Ethernet. Okay, and it uses the standard BNC connectors, or the British Naval connectors, or the Bayonet Neil Concealment connectors. But there is difference between the thick Ethernet and thin Ethernet. Though the thin Ethernet is cheaper and easier to install and is flexible to work with, it could run only for 185 meters per segment. It can only, the maximum segment length for thick or thin Ethernet is 185 meters compared to the 500 meters of your thick Ethernet. And also, you can actually connect only 30 machines per segment of thin Ethernet, whereas you can connect up to 100 machines per segment of your thick Ethernet. So each version of this Ethernet has a maximum cable length per segment. So in case of thicknet, you have 500 meters. In case of thinnet, you have a maximum segment length of 185 meters through which the signal can propagate. Now, if you want to create a large network, these segments have to be connected with one another, right? So to allow larger networks, these multiple cables can be connected by repeaters. So what are these repeaters? So the repeater is a physical layer device that receives, amplifies, which is nothing but it regenerates the signal to its original value and transmits the signals in both the directions. So Ethernet, as I told you, there is a maximum cable length per segment, and if you want to connect a larger network, these segments have to be connected using different repeaters. And finally, for each of these cables, the information was transmitted using the Manchester encoding scheme. So the Manchester encoding scheme, where you actually send each bit by using a signal which has an inversion in the middle. That means one is actually transmitted using the pair of either high to low or low to high. 0 is sent using same, either one of these things. So Manchester encoding requires that for each bit, when you are transmitting each and every bit, there is always one transmission in the, or one transition in the middle. Okay. Now moving on to the frame format. So what is this Ethernet frame? A Ethernet frame is the protocol data unit of the data link layer. So a data link layer on one machine actually exchanges a Ethernet frame with the data link layer on the other machine. The sender, the sending DLL transmits an Ethernet frame to the receiving DLL. So as I told you, first initially the DEC, Intel and Xerox companies, they have come up with a DAX standard. So I'm showing both the standards here, both the DAX standard and also the IEEE 802.3 standard. So both of these frame formats do start with something called as a preamble, and then you have the two addresses which will identify the destination and the source, followed by the type or the length fields. This is the one more differentiation between the DAX format and the IEEE 802.3 format, and the remaining ones are the same. We follow it with the data and a padding field, and followed up by the checksum field. Okay, so let's talk about this particular part. What is this preamble? And there is also one difference you can see here. In the DAX format, the preamble is 8 bytes, which is nothing but 8 8s are 64 bits. Whereas in IEEE 802.3 format, the preamble is of only 7 bytes, followed by something called as an SOF. SOF actually stands for start of the frame delimiter. Sometimes in some textbooks, it is also written as SFD, which stands for start of the frame delimiter. Now, what is this? What is the difference between that? Let me show you. So preamble is nothing but it is of 8 bytes containing the sequence of alternating ones and zeros. So 10, 10, 10, 10, 10. Why do we need it? It actually serves the synchronization purpose. For Ethernet to work properly, clock synchronization is mandatory between the sender and receiver. So whenever the sender is going to put data on the wire, the receiver should be synced with the sender to receive that particular data. To maintain the synchronization, each and every frame will have a preamble to it. So this preamble, when you implement the Manchester encoding for this pattern, it produces a 10 megahertz square wave for exactly 6.4 microseconds, which allows the receiver's clock to synchronize with that of the senders. So preamble is used for synchronization between the sender and receiver, and the synchronization information is sent along with each and every frame of Ethernet. So they are required to stay synchronized for the rest of the frame using the Manchester encoding to keep track of the bit boundaries. Okay. Now, as I told you, in DAX standard, the preamble is of 8 bytes. But for IEEE 802.3 standard, the preamble is of 7 bytes plus 1 byte, which is called as SOF byte. Now, the SOF, or in other words, the start of the frame delimiter byte, it is nothing but it is the same pattern except for the last bit. Only the 8th bit is changed. This is a 1 byte field which is always set to 10101011. So the same pattern is being repeated except for the last bit. Instead of a 0, now we are placing a 1 here. It is designed to break the bit pattern of the preamble and signal the start of the actual frame. So that is the reason I say it. We call it as the start of the frame delimiter. The SFD is immediately followed by the destination MAC address, which is the first field in an Ethernet frame. Most people will feel that preamble is also a part of the Ethernet frame, but it is not true. The actual Ethernet frame starts from the destination address field only. Then you might ask me, sir, why did you show preamble here? Because each frame consists of the synchronization data. Preamble is also shown as part of your Ethernet frame. But for calculation purposes, the Ethernet frame actually starts from the destination address field. So this is how your preamble looks like in an IEEE 802.3 format. So all these are 1, 2, 3, 4, 5, 6, 7. 7 bytes of alternating ones and zeros. And for the last 8th byte, which is your SOF byte, once again, you have alternating ones and zeros except for the last bit here. Okay. So this is your preamble. This is your SOF. All put together, it looks like this. Now, what is this destination address? You know that in data link layer, we use something called as a MAC address. We also call it as a physical address or Ethernet address. So this 6 byte field is the identifier for the intended recipient. So to whom you are going to send your frame to is actually identified by the destination MAC address field. So the end nodes are identified by their Ethernet addresses, which we call it as a MAC address or hardware address. This is a physical address and it will not change. Unlike the IP address, which changes according to the point of attachment to the network, MAC address will not change for a particular device. So out of the 6 bytes of a MAC address, the first 3 bytes are called as OUI, or organizationally unique identifier, which is actually assigned by IEEE, and they identify which is the manufacturer for this particular device. The remaining bits are actually assigned by the manufacturer itself. Okay. So the first 3 bytes are your OUI and the last 3 bytes are unique for every host or the device. So you can see this is the common format of MAC address, which we usually write it down or read it in hexadecimal format. So of these are the first 3 bytes which give you your OUI, and the remaining 3 bytes are used to uniquely identify this particular machine. Okay, so altogether 6 bytes, which gives you a 48-bit MAC address. Now, the first transmitted bit of the destination address is a 0 for ordinary addresses. You might ask me, sir, what do you mean by an ordinary addresses? 0 stands for unicasting. That means if I am sending this frame to one particular destination, then I put a 0 here. Or else I can put a 1 for group addresses, which is called as multicasting. Okay. So if I am sending a frame from one sender to one destination, we call it as unicasting. And if I am sending a frame to a group of addresses, then we call it as a multicasting. So group addresses allow multiple stations to listen to a single address. So I can give a group address. So for this group address, a frame which is destined to this group address can be taken care of or can be shared among these multiple stations which belong to that particular group. So when a frame is sent to a group address, all the stations in the group receive it. Sending to a group of stations is called as multicasting. The special address consisting of all ones is reserved for broadcasting. Now, if all the bits here, if all the 48 bits of this MAC address are ones, we call it as a broadcast address. What do you mean by broadcast? Sending it to everyone. So we discussed unicast, we discussed multicast, and now I'm talking about broadcast. So broadcasting means it is sent for everyone. So if I put ones in all the 48-bit positions, then we call it as a broadcast address. Why is it used? If a frame containing all ones in the destination field, this frame is actually accepted by everyone which is connected to the media. So a broadcast frame is accepted or received and accepted by all the stations on that particular network. Okay. The next field comes is your source MAC address, which is once again a 6-byte MAC address which identifies the source or the sender of this particular frame. So there are two addresses. The first one is a destination MAC address, which tells you to whom this frame is going to. And the next one is a source MAC address, which tells you which is the source for this particular frame or who is the sender of this particular frame. Okay. Next thing. Now we have two fields. Of course, both of them are 2 bytes. One of them is called as type field. The other one is a length field. In case of DIX standard, we discuss about the type field, and in case of IEEE 802.3 standard, we discuss it as a length field. Of course, the type field is going to identify the upper layer protocol encapsulated in the Ethernet frame. That means that once the receiving's data link layer, once the receiver's data link layer gets this frame, it has to understand to which protocol should this frame be handed over in the network layer. So it might be IPv4, it might be IPv6 packet, or it might be an ARP packet. So to which higher layer protocol should this payload be transmitted or be given to is determined by the type field. So based on the value in the type field, the receiver's data link layer will be able to understand which type of packet it is or what is the payload and to whom it should forward this to. If you are talking about the length field, in case of IEEE 802.3 format, it specifies the length of the data field. So how much is the data field? What is the length of the data field in bytes is actually given in the place of length field. Now you might ask me, what is the requirement of length field? Why should I bother about the length of the data? Because Ethernet uses variable sized frames. It is not a fixed frame size. So it might have multiple frame sizes. So in order for the receiver to understand what is the total length of your data field, this particular length field is used. So whichever value you place it here, that means that that many number of bytes are present in your length field. Now let us talk about the data and padding field. You might ask me once again, sir, why are you mixing two things? What is the need for this padding? Because please remember the fact that there is a minimum length that is required for each Ethernet frame. Any Ethernet frame must not be less than 64 bytes in length. I will discuss why that 64 bytes length is required, or where did you get the 64 bytes from. I will discuss that. But for that reason, for a frame to be a minimum of 64 bytes, if you count the number of bytes or the mandatory fields in your header, this is 6, this is 6, the length is 6, and the CRC, which is your last field, which contains the CRC32 frame check sequence, is 4 bytes. So 6 plus 6, 12, 12 plus 2, 14, 14 plus 4, 18. So for a minimum of 64 bytes, if you minus the 18 bytes of mandatory header, which will give you 46 bytes, right? So your data field must be a minimum of 46 bytes. If it is less than 46 bytes, your total length of the frame will be less than 64 bytes and it will not be considered. Now, any frame less than 64 bytes in length is considered as a collision fragment. You know that in CSMA CD, we discussed earlier, in CSMA CD, if a station listens to a collision or if a station detects a collision, it will abruptly end the transmission. It will not transmit the whole frame because anyhow it has collided, anyhow it has to be retransmitted again. So what is the purpose of transmitting it? So a station, once it detects the collision, it will abruptly end its transmission. So what is going to happen to those transmissions which are cut off in the middle? So any station which receives a frame which is less than 64 bytes in length will not be considered. These frames are called as runt frames and they are automatically discarded by any receiving station. Only a frame which has got more than 64 bytes of length will be considered as the frame. Okay, anything less than 64 will not be taken into consideration and will be discarded. So for this particular reason, a frame to be of 64 bytes in length, if you remove the headers of 18 bytes, your data and padding fields must be 46 bytes. But in cases, if your data, if there is no data at all, if you are sending an acknowledgement frame, there is no data in it, then the total length of the frame will be less than 64. For that purpose, that is the reason I'm saying we are adding something called as a padding. This padding is used when the length of the data field is less than 46. If your length of the data is more than 46, then you need not bother about padding. If I say if the data is 0 bytes, then padding will be 46 bytes. If the data is 10 bytes, then your padding will be 36 bytes. If your data is 100 bytes, don't worry about padding because it is more than your minimum length. So in order to maintain the minimum length of the frame as 64 bytes, I am adding padding here. Okay. So the minimum frame length is 64 bytes and the maximum frame length is 1518 bytes. So the maximum payload length which can fit inside a frame is Ethernet frame is 1500 bytes, and this 1500 plus your 18 bytes of header, which will give you the maximum frame length to be 1518. Of course, in some cases, special consideration can be given to frames that are more than 1500 bytes in length. Such frames are called as jumbo frames. So frames which are less than 64 bytes are not considered and will be discarded. They are called as runt frames, and frames which are more than 1500 bytes in length are called as jumbo frames. Now, to answer my earlier question, why should I keep the minimum length as 64 bytes? What is the purpose? For this, you have to think about the CSMA CD implementation of Ethernet or the MAC protocol, which is your carrier sense multiple access with collision detection. If you remember the functioning of CSMA CD, a station while transmitting has to listen to the medium also. So whenever a station is transmitting data, it has to keep listening to the medium. So if it is inputting something and if it listens something else, it will automatically assume that a collision has happened, right? Then it will abruptly stop the transmission. It will do some backoff mechanism, and then it will retry or retransmit after some time, right? So one important factor for minimum length frame is to prevent a station from completing the transmission of a short frame before the first bit has even reached the far end of the cable where collision may happen. In order to understand this, let me show you an example. Let us consider there are two stations, A and B. Okay, both are at the two far ends of your cable. Now, if you implement CSMA CD, let us assume that A has started its transmission at t is equal to 0. Now, this is A's frame. Okay, for this frame to reach B, let us assume that it is going to take t seconds. And unfortunately, before this t seconds, B tried to sense the medium, and B assumed that the medium is idle and it has also started its transmission, which leads to a collision here. Okay, now for A to detect this collision, A have to be active or A has to be listening onto the medium for this collision to be coming back to A. So this collision, if it is to be heard by A have to be remain active till 2t seconds, right? So for this transmission to go to B, it takes t seconds. And if there is a collision that happens at B, for this collision to be heard by A, it takes another t seconds, right? So onward journey, return journey, t plus t gives me 2t seconds. Now, what is the requirement here? Now, my requirement is that A's transmission of frame or A's frame must have enough information such that A must be still transmitting at 2t seconds for it to be listening to this collision. For A to listen to this collision and know that a collision has happened, it has to be transmitting even at 2t seconds. Okay, from that calculation, let us try this. Let us assume A as our sender and it starts transmission at time 0. This transmission reaches B at t, where collision happens, and this collision can be heard at A only at 2t. Now for this to happen, A has to be listening at 2t. If A has assumed, let us assume that maybe before even 2t, A has finished the transmission, and A will assume that because it still didn't hear any collision, it will mistakenly assume that this frame has been reached without any collisions, or successful transmission of frame is done. But that is not the case here, right? So A must still be transmitting at 2t to detect this collision. Now for this to happen, now let us take the standard LAN, which is of 10 Mbps. So at 10 Mbps speed, and with our specification telling the maximum length of a local area network to be 2500 meters using 4 repeaters. Using 4 repeaters, the round trip time has been determined to be nearly 50 microseconds in the worst case. That means the length of the frame must be at least some value, which while transmitting from A, the A should be active for at least 50 microseconds. If this is the case, at 10 Mbps, 1 bit will take 0.1 microsecond. For A to remain active, or for A to stay on the line transmitting at 50 microseconds, you require how many bits? So 1 bit will take 0.1 microsecond, right? And now for 50 microseconds to be active, how many bits it should be there? The least number of bits that your frame must be having is 500 bits. So unless until the frame length is 500 bits, A's transmission will be less than 50 microseconds. So if A's transmission is less than 50 microseconds, there is a high chance that A will not be listening to the collision that might happen at the other end of the medium. So rounding off the 500 bits to 512, which is 64 bytes, you got the minimum length of the frame. So of these 64 bytes, you have your 14 byte header, you have your 46 bytes data or padding, and your 4 byte CRC. So this is why we got the minimum length of the frame as 64 bytes. Okay. Now, so this is how you decide from the CSMA CD's implementation, where the sender has to keep sensing the medium while transmitting. It has to keep sensing the medium while transmitting. So for A's transmission to be active, such that any collision happening at the other end of the wire to be heard by A, the minimum length of the frame that A is transmitting must be at least 512 bytes, or sorry, 512 bits, which is equal to 64 bytes. Okay. Now, the last field is your CRC field, or your frame check sequence field, which is used for error detection. We use the CRC32 method, or the CRC method that we discussed in our earlier videos, to ensure the integrity of the data. Error control is maintained. So once you take the entire frame, perform the CRC calculation, put those 32 bits of CRC or the 32 redundant bits at the end of the frame, such that the receiver can perform the same calculation again and see if there are any errors within the transmission. If there are any errors, the frame have to be retransmitted. Okay. Now, before we close, we have discussed all the fields in your frame format, right? We discussed about preamble, we discussed about the start of the frame delimiter, then we discussed about the destination MAC address, then we discussed about the source MAC address, we discussed about the type field, then we discussed about the length field, followed up by the data and padding field, and then your CRC field. The last thing is, in case of Ethernet, we use something called as an binary exponential backoff algorithm. This is used in conjunction with your CSMA CD algorithm. So classic Ethernet uses the one persistent CSMA CD algorithm, where stations sense the medium when they have a frame to send, and send the frame as soon as medium becomes idle. That means if there are multiple stations that are waiting for the medium to become idle, they keep on sensing the medium. They continuously sense the medium. So at a point, once the medium becomes idle, all these stations try to transmit at the same time. What would this result in? When multiple stations try to transmit simultaneously, this leads to collisions. These collisions are actually heard by all the stations. So what happens when a collision happens? Each of the stations will wait for some random amount of time and they will try to retransmit again after that particular random amount of time. So they monitor the channel for collisions as they send. If there is a collision, they abort the transmission with a short jam signal and retransmit after a random interval. Who decides this random interval? Who decides this random interval? How can you say what is a random interval? How do you choose a random interval? For that purpose, we use the binary exponential backoff algorithm. So this binary exponential backoff algorithm uses time slots. So the time is actually divided into discrete slots whose or each slot length is equal to the worst case round trip propagation time, which is 51.2 microseconds. Let me take a small example for you first, explain it, and then I will show you how this is being done. Now assume that there are two stations A and B which want to transmit data. Now initially both of them try to sense the medium at the same time and both of them sense the medium to be idle and both of them transmit. So when both try to transmit, what happens? A collision happens in between. Okay, and this collision is heard both by A and B. So because this is the first instance of collision at both the stations, what will happen is A will now select a random number. The random number is selected in such a way that 0 to 2 power k minus 1. What is this k? K is the number of retransmissions that you are doing. Because this is the first one, A has to select from 0, 1 because 2 power 1 minus 1. Similarly, B will also select from 0, 1. Unfortunately, let us assume that A has selected 0, B has selected 0 only. That means they do not want to wait any longer. So immediately they try to transmit again after waiting 0 seconds. Immediately. So what will happen? Again collision will happen. Now K is equal to 2. Here K is equal to 1 because this is the first attempt. For the second attempt, K will become 2. So using this formula, 0 to 2 square minus 1 will give me, now A will have 0, 1, 2, 3. Similarly, B will have 0, 1, 2, 3. So let us assume that A has selected 2 and B has selected 1. Now what is this? So now A will wait for 2 into 51.2 microseconds and B will wait for 1 into 51.2 microseconds. So your random number into that many number of slots. So now what will happen? After one slot, B will start its transmission, success. After 2 slots, A will start its transmission, success. This is called as binary exponential backoff algorithm, where multiple stations, when they try to transmit at the same time, will lead to collisions, and each one of the station, after detecting the collision, they can select a random number such that they can manage their retransmission times. So how much time do they need to wait? So the delay time is selected using the binary exponential backoff algorithm. For the first attempt, choose K from 0, 1 because K is calculated from this formula 0 to 2 power n minus 1, or n is the number of attempts that you are doing. Sir, you can ask me, sir, how many times can you do this? Can you keep on doing it? No. After 10 collisions have been reached, the randomization interval is frozen at a maximum of 1023. So even if there are 10 collisions that are happening, okay. So in that case, what will happen? 2 power 10 is equal to 1024. So 0 to 1023. This is the maximum randomization that any station can go for after 10 collisions. And even if after 16 collisions also nothing is happening, so you tried for 16 times, that means K is equal to 16. So at K is equal to 16 also you are not getting a positive response. Then that means that there is some error with the cable or something else, and you leave it up to the higher layers. The data link layer will say that, sorry, I can't transmit anymore. Please take care of the problem. So After 16 collisions, the controller throws in the towel and reports failure back to the computer. Further recovery is up to the higher layers. If there is no collision, the sender assumes that the frame was probably successfully delivered, because you know that the collision assumption, if there is an error, that error is only because of collision. Any errors caused is only because of collision. Okay, and that is neither CSMA CD nor Ethernet provides acknowledgements. Of course, there is no need of acknowledgements because the probability of an error happening is very less in case of Ethernet. Okay, so this is how CSMA CD works, and this is how binary exponential algorithm works. So each station, based on the number of attempts they are making, will select one slot, will select a random number, and that random number into 51.2 microsecond slots, it will wait, and after waiting that particular time, it will try to retransmit. If there is a collision, it will once again select another random number and will wait for some more time, and it will try to retransmit after that time. So this is how your binary exponential backoff algorithm works in case of Ethernet. So hopefully you have understood the format of 802.3. What are the fields that are there in the 802.3 standard frame format, and how the binary exponential backoff algorithm works. So thank you very much for watching, and do subscribe and share. Thank you.